Hi, in this video I'm going to show an example problem of free fall. This is also a constant acceleration problem, and I'm going to show you a few more higher level things about constant acceleration here. So this is a little bit more detailed here. Be sure that you've gone and already worked a few constant acceleration problems. You've seen my previous video on constant acceleration. So in this case we have an object that is moving in the air straight up and down, and the influence is only the gravitational acceleration. So if you have this case, you can always know that the acceleration A, it's going to be minus g. Now g, as you've learned, is equal to 9.8 meters per second squared, and moreover, g, the acceleration due to g, it always points straight down. So what we say here is that the acceleration A is equal to minus g. G is just a positive number, 9.8 meters per second squared, so we put the negative sign in front. So this is always the case if you have free fall. We know exactly what the acceleration is. It's constant. It's equal to negative 9.8 meters per second squared. Now, in this problem and free fall problems, we're still one-dimensional, except that now the line goes up and down. So if I draw my axis here, I'm actually looking at something like this. And we choose plus y to be the upwards direction, and so there's up and down there. And now I'm free to choose the 0 position of the y-axis wherever I want. I might want to put it right here, call that 0. Or I might want to put it at the bottom of the building, call that 0. In fact, I'm going to do that. I'm going to just call this here y equals 0 at the bottom. Now let's read this quickly. A ball is thrown from the top of a building with an initial velocity of 20 meters per second straight upward, at an initial height of 50 meters above the ground. The ball just misses the edge of the roof on its way down. Determine the time needed for the ball to reach the ground and the velocity which it strikes the ground. So a couple things here. It's true that the person initially is throwing the ball up, and at the very end the ball hits the ground. In free fall, however, we ignore the instance in which the ball is in the hand and as it hits the ground. Those things include other accelerations besides gravity. Instead, the hand, all it does is serve to set the initial velocity. And when we think about the final velocity before it strikes the ground, we're talking about just the instant before it strikes the ground. Of course, once it hits the ground, everything changes. So since I know this is a constant acceleration problem, I've set this up in the way that we do constant acceleration problems. I've got my 5 variables, and now I want to gather my information. Well, let me go ahead and see that we start here. So here's our y initial. It equals 50 meters. And down at the bottom is where it ends, right? So here we go. Start. We go up, we come down, and then we're going to end down here, right? All we care about are the endpoints of the motion for these type of problems, right? So at the very end, we know what our final position is. Y equals 0 meters, right? And now we can calculate delta y. Y final minus y initial. That's going to be 0 minus 50 meters, which gives us a negative 50 meters. And notice that since the ball between the start and end points, it has gone down, the displacement is negative, it's in the negative direction, hence the minus 50 meters. Now for the initial velocity, we see that it's 20 meters per second, it's thrown up, so that's going to be a plus 20. And we don't know what the final velocity or what the time interval is that it takes to reach the ground. We're trying to find these two things. Now we're going to go ahead and look at the equations to figure out which one we should use. Now I might pick to solve for delta t first. In that case, I want to pick the equations that don't have v final. Let's look at them real quick. So suppose I want to try this one here. Doesn't have v final, this equation. Now if I think about it, I know what delta, well in this case the x's should be considered y's now. So I know what delta y is. I know what v initial is, I know what a is, but notice that I still have 2 delta t's, and this one is actually squared. If we want to solve the problem using this equation, we're going to have to use, whoops, get out of there, we're going to have to use a quadratic equation, right? And you can do it like that. You'll get two answers for delta t. You'll need to pick the one that's physically relevant, which is the one that's positive probably. But I'm going to show you a different way to do it. Instead of doing the quadratic equation, let's avoid the quadratic equation. If we want, instead of solving for delta t first, let's solve for v final first. Then I need the equations that don't have delta t. Let's look at this one over here. Aha! We can use this one here to solve for v final because we know v initial, a, and delta y. So let's go ahead and use this equation on the to solve for v final. So we'll go ahead and write down the fifth equation right over here to solve for v final. So here's the fifth equation. V squared is equal to v initial squared plus 2a delta y. And I just replaced the x's with the y's here. We want to solve for v final. Well, you know what? We've got all the information here. We just need to go ahead and plug it in and take a square root. So v is going to be equal to the square root of all those numbers, right? I'm going to put in my v initial and square it. So I've got 20 meters per second squared. And then I'm going to go ahead, add that 2. Now notice I need to put the signs in accurately. So I got a minus 9.8 meters per second squared for the acceleration. And for the delta y, we've got minus 50 meters. And let's go ahead and close that. Let's see what we get when we put this into our calculator. What do we get? I get a 37.1 meters per second. You should check out your units and see that they work out. I've got one term here in the beginning that's got meters per second. We need to square it. So if we go ahead and square our meters per second, then we square root it. Well, the square root undoes the square, comes out to meters per second. That's exactly what we want. Good. Now, one other question though. Down here at the end, which direction is the ball moving? Is it up or down? Is the velocity upwards, positive, or downwards, negative? Well, it turns out it must be going down right before it hits the ground, so it must be negative. What did we miss here? Whenever you take a square root, actually, you should put plus or minus in front of the square root symbol. And it's up to you to choose which of these two is physically correct. Look at the picture. Think about it. We know it's going down, so it's not the plus, it's the negative sign, and we're going to put that in there. So now we know what the final velocity is, the instant before it strikes the ground, right? All right, now we can go ahead and go back and solve for delta t, and we can use any of the equations now because all of a sudden now we know all 4 of the variables except for delta t. Let's go back and choose an equation that we can use to solve for delta t. And how about we do the first one? That one seems like an easy one, right? So let's go back here and we'll write down that equation, which is v final equals v initial plus a delta t. We want to solve for delta t. Let's do a little bit of algebra. So a times delta t is equal to v minus v initial. Divide both sides by a, and we're going to end up getting delta t that we're looking for here. And so delta t in this case is equal to v minus v initial divided by the acceleration. We have all those numbers. Let's go ahead and plug them in. V initial, 20 meters per second. Oops, I got that backwards. That's not v initial. That's v final. So v final minus 37.1 meters per second minus v initial, 20 meters per second, divided by a minus 9.8 meters per second squared. And when we go ahead and put this in the calculator, we'll get our answer for delta t. And putting this into the calculator, we find out that delta t is equal to 5.83 seconds. Positive number, that's good. What are the units? Seconds, we know it should be seconds. Is that true? Let's check it out here real quick. So we've got in the numerator, meters per second. In the bottom, we've got meters per second squared. Complex numerator denominator, that means we can take the numerator, multiply by the reciprocal of the denominator. Meters cancel. We got 2 seconds on top. One of them cancel. We're left with seconds. Looks like that's exactly what we want.